So now we continue talking about probability by talking about empirical probability, which is also known as statistical probability. And it's based on observations obtained from experiments. So the way we find empirical probability is we take the total number of frequency in some event, and we divide it by the total number of frequencies altogether. So if we look at example 6, it says that a company is conducting a telephone survey of randomly selected individuals to go get their overall impression of the past decade. So far, 1,504 people have been surveyed. The frequency distribution shows the results. What's the probability that the next person surveyed has a positive overall impression of the 2,000? So I look at the frequency distribution table we have, and we look for positive results, which in our case is 406. And I take that number and I divide it by the total number of people who have responded to the survey, which would be 1,504. I go to my calculator and divide these out, and I end up getting 0.27. Here's another example that you can try if you'd like. Example 7 says using frequency distribution to find probabilities. You survey a sample of 1,000 employees at a company and record the age of each. The results are shown in the frequency distribution at the left. If you randomly select another employee, what is the probability that the employee will be between 25 and 34 years old? So I go over here and I find 25 to 34 years old, which is a frequency of 366. I divide that by the total number of employees at the company and find that it ends up being 0.366%, which is about 36.7%. Here's another example as well. So we look back and we say, okay, so classical probability is where you take the number of outcomes in an event divided by the total numbers in the sample space. Empirical probability is where you actually look at some frequency of some experiment. You take the frequency divided by the total number of events. The last type, the third type of probability, is called subjective probability. And subjective probability results from intuition, educated guess, and estimates. And so we can kind of do this after a while. You can kind of see something. If something is over 90%, you probably more likely it's going to happen. Something kind of like that. Now it says right here, classify the types of probability. Classify each statement as an example of classical probability, empirical probability, or subjective probability, and explain your reasonings. So it says right here, the probability that you will get the flu this year is 0.1%. So what type is that? Well, it's kind of just an educated guess because it's pretty small. It's about 10%. So are you going to get it? Probably not. So this is subjective probability. Next one, the probability that a voter chosen at random will be younger than 35 years old is 0.3. So I look at that and I'd say, okay, so most likely what they did is they surveyed voters and their age groups. So just like in example 7, that was an example of empirical probability. And finally, the last one, the probability of winning a 1,000 ticket raffle is 1 out of 1,000. That right there is good old classic probability. The reason that is, there's 1,000 tickets. You have one of them, 1 out of 1,000. That's classical probability. So, the range of probability rule says this. The probability of any event is between 0 and 1 inclusively, meaning that your probability is some decimal between 0 and 1. So you'll always find the probability between those two numbers. Now if you look right here, this isn't in your notes, but I wanted to show you that if something is at 0%, it's very impossible for something to happen. Where if something is at a probability of 1, it's certain going to happen. Then we have an even chance at 0.5, which is like 50%. Anything less than that is unlikely. Anything more than that is a likely event happening. So, complement of an event is our next definition. And essentially it says if the set of event E is the set of all outcomes in a sample space, then those not included in event E would be the complement. And so we denote it like this, E with an apostrophe, known as E prime. And you'll notice that the probability of event E happening and the probability of E not happening, or E prime, is always going to be 1. So that's kind of nice to know. So example 9 says use the frequency distribution in example 7 to find the probability of randomly choosing an employee who is not between 25 and 34 years old. Well, if we look back, the probability of choosing someone between 25 and 34 years old was 0.366. So the probability of not choosing someone who is in that age range would be 1 minus 0.366. So I go to my calculator and I take 1 minus 0.366 and I find it to be 0.634. So the chances, the probability of not choosing someone between 25 and 34 years old is 0.63%. So which is more likely, choosing someone between 25 and 34 or not choosing someone between 25 and 34? And since it's greater than 50%, not choosing someone is greater. The last one, using a tree diagram. Probability experiment consists of tossing a coin and spinning the spinner shown at the left. The spinner is equally likely to land on each number. Use a tree diagram to find the probability of each event. So tossing a tail and spinning an odd number. So what I can do is I can create a tree diagram. And the nice thing is they've kind of already created one for us right here. So you go to your coin and I can either get heads or I can get tails. And from heads, then I can either get a 1, 2, 3, 4, 5, 6, 7, 8. And so these are the number of outcomes right here, H1, H2 to H8. But let's say I flipped my coin and I got a tails. Then right here would be my possible choices, tails 1, 2, so on through 8. So it says tossing a tails and spinning an odd number. So what we can do is we can go down here to tails and circle all the odd numbers that we have. So tails with a 1, tails with a 3, tails with a 5, and tails with a 7. So there's a total of 4 outcomes. 4 out of the total number of outcomes, which would be 16. The probability of that happening then is 0.25. Next, event B, tossing a heads or spinning a number greater than 3. So if I'm tossing a heads, that means I have all 8 of these as options, because those all have heads in them. And then it says, or spinning a number greater than 3. Well, 4, 5, 6, 7, 8 are already taken with the heads, so we have to take 4, 5, 6, 7, 8 with the tails as well. So that's a total of 8 plus another 1, 2, 3, 4, 5. So 8 plus 5 would be 13 out of 16. And so I take that and I say, okay, well 13 divided by 16 is 0.8125, a more likely scenario. So we've used our tree diagram that we created to find our probabilities. There's an example that you can try as well. The last example we have for today. Your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability your college identification number when randomly getting your college identification number when randomly generated 8 digits? So essentially what they're saying is if you randomly generate 8 digits, what would it be? Well, this goes back to something we talked about earlier. So the fundamental counting principle says this, okay? The first number I could get out of my 8-digit number, I can have 0 through 9, and it can be repeated. So then for the second number, it's also 10. Third number can be 10, fourth 10, fifth 10, sixth 10, seventh 10, eighth 10. Okay? Multiply all of those together is 1 with 8 zeros. Okay? Now, how many college identification numbers do you have? Only 1. So your chance of getting that is 1 out of it would be 100 million. Not very good odds. If you put that as a decimal, it would be super small. Here's your assignment to finish up for today. It's page 138, 35 through 50, and 52 through 72